Hey everyone, so I'm going to be talking a little bit about the Web3 identity stack. So first of all, just a little bit about myself. My name's Nich. I'm currently doing head of platform and research work at 1KX, and I'm also a contributor at Meta Gamma Delta. And in the past, I was a smart contract dev at Upstate Interactive and Mochi community. So just a little bit about what we'll be covering today. We're going to go over the evolution of identity on the internet, the core concepts in decentralized identity, and I'll give a layer-by-layer overview of the decentralized identity stack from blockchains and verifiable data registries to decentralized storage, through to wallets, authentication, authorization, and attestations. Okay. So first, just to define identity a little bit, broadly speaking, identity is an emergent property that consists of data associated with a person, or it can be an entity or an object. So in the physical world, we kind of hold these loose associations around as mental associations in our heads. But in the digital world, this is formalized into two components, which is the identifier, which is the unique set of characters or numbers that identifies a subject, and then the data associated with that subject. So it could be anything from your passport number, which is associated to your travel history, your student ID, contains links to your academic achievements, your bank account, to your financial history, Twitter to your tweets, and so on. So why are we talking about decentralized identity today? And why is this important? So for individuals, the DID stack allows us to take back control of our identity. So we no longer have to depend on centralized gatekeepers and identity providers like Google, Facebook, and Twitter. And we can selectively disclose, choose what attributes of our data we want to share instead of just having that be in the hands of centralized IDPs. And the credentials are tamper-proof, and they're stored on a wallet in your device where it's portable and shareable. So if you're interviewing for a job, for example, you can show your university degrees and achievements right there, and it's verifiable by the person that's consuming that data. So for organizations, you can verify information without contacting the issuer to verify the authenticity of the information. It prevents certificate fraud, right? Because credentials are immediately verifiable using cryptography. It reduces the risk of being targeted by attacks by storing less user data. And for developers, it allows you to build user-centric dApps that enhance the user experience because you're safely requesting data directly from the users while maintaining their privacy. So just going over the different eras of identity on the internet. So in the 90s, early 2000s, the accounts are managed by applications. So it's very application-centric in terms of, you sign up with your username and password. It's very poor UX for the users because across applications, you have to create a new account. And there's low security because you end up repeating the same password, like a memorable, guessable password, and it's fractured, right? So the reputation that you build up on one platform is not easily transferable to another platform. You have to keep authenticating yourself with the username and password each time. And then came federated identity, which is kind of the perversing paradigm that we're in today, where you create an account with identity providers like Google and Facebook, and then log into applications with social login, OAuth. So in terms of UX, it's a big improvement from the previous era. And it's semi-portable in terms of if you're storing your data with Google, you can share some of your information with the new service that you're signing up for. But it's centralized, so your data is actually in the control of these IDPs. So now we're in the decentralized paradigm where it's managed by P2P relationships with no sort of special privileges to any one party. So in the eyes of the registry, these peers are treated the same. which allows us to have self-sovereign identity and a user-centric experience for dApps. So these are some of the technologies we'll be going over in a bit. So just zooming into that, this is generally how like the stack kind of comes together. You have your verifiable data registry, DIDs, and then you're making authentication, authorization requests to the applications on top. So your identifiers are typically issued and stored on data registries like blockchains or decentralized storage infrastructure. And then you're making claims about each other, either your peer or yourself, via attestations. And then the verifications are done using cryptographic signatures. So that's the yellow arrows there. And then the technology that puts all of these pieces together is decentralized publicly infrastructure. So you hold your keys in your wallet, and it's used by identities, individuals, communities to authenticate, prove ownership of assets, and manage your DIDs. So there's over 100 DID methods that's listed on the WC3 website, and it's often associated with their own blockchains or VDRs. So on Ethereum, there's one where your account is your pseudo identity. Cosmos represents their interchain assets as an identity. And then on Bitcoin, there's one as well. And then there's new or emergent DID methods like PKH, which is more ledger agnostic, where it resolves to the chain in the background so that you can just have one key and multiple identities on each chain. So just a quick anatomy of a DID. So the DID scheme kind of tells systems that you're referring to an identity and not something else like an email or a URL, a website. And then the method is like which registry you're on. And then the identifier is your unique identifier within that registry. And then it resolves to a DID document, which contains all the information about you and the authorization, how you authenticate yourself. So in terms of decentralized data storage, we have blockchain-based storage like Ethereum and Arweave, where the data, so the intuition here is that each full node has to store the entire chain and users pay transaction fees based on demand. But Ethereum is unsuitable for most data due to high gas costs and lack of privacy, because data is immutable by default. Arweave is another blockchain-based example of decentralized storage where you're uploading onto Arweave and you're paying a one-time fee, and your data is guaranteed to be stored permanently. And then there's contract-based data storage like IPFS, Filecoin, Storj, that intuits that data can't be replicated and stored across all nodes. And instead it uses contracts or like service-level agreements, let's say, with multiple nodes who agree to hold your data for a specified period of time. In terms of how you update these data, so the examples that we gave before works well with immutable data, but most of the applications we interact with today, you want to update your profiles and contributions and things like that, right? So the Web3 protocols that are designed for mutable data enable updates whilst leveraging the decentralized storage layers underneath. So for example, Ceramic takes immutable files that are stored in IPFS and builds a mutable layer on top of it where you can update your profile, and it gives like a snapshot or a data stream. And then when applications read from the Ceramic stream, it gives the latest updated data. Tableland is another example where you're essentially minting databases as NFTs. Okay, so the wallets. So the wallets here are essentially, broadly speaking, an interface where you're doing all these actions. So it's an interface and all the underlying infrastructure for key management, communications, how these issuers, holders, verifiers are making claims about each other. And so there's, it's worth making a distinction here between crypto wallets like MetaMask and identity wallets. So crypto wallets right now aren't really designed to make claims about another identity. They're designed to hold your assets and sign transactions, and they're typically specific to a blockchain network. So you use MetaMask for EVM chains and Phantom for Solana, for example. On the other hand, identity wallets store identities, and they're more kind of compatible with the diagram we have here. So it allows users to create and present claims so that they can present their identity data across apps and services. So these are some examples of identity wallets. Polygon ID has a wallet where you can store your credentials, like membership and your proof of personhood if you've done KYC or used something like Gitcoin Passport. And so typically these wallets hold is where you keep your verifiable credentials. In terms of authentication, authentication essentially is the process where you're confirming your identity based on more authentication factors. So these can be a digital signature, your ID card, a security token, or in the kind of Web1 paradigm where you're putting in a password. So in Web3, the wallets just use the key that they store to produce a signature that serves as a proof that the holder owns the private key that's associated with the account that you're signing in with. So this is a nice little graphic to show kind of the evolution here. So in Web1, you're kind of with your username and password. Right now, most people are using social logins, and then with Web3, it's going to be log in with your wallet. So authorization typically comes with the flow of authentication, but it's a separate process. So while authentication, you're proving that you're you, authentication tells the application what data and what resources pertaining to you that they can interact with. So in federated identity, you're allowing Google to authorize third-party applications to view and update your data stored with them. But in decentralized identity, it achieves the same thing. But your wallet, you're making a permission with your wallet to grant the right to each third party without centralized middlemen. So these are examples of authorization prompts that we've seen in Web 2. Then attestations, credentials, some terminology here. Attestations are just claims that certify that a claim and signatures are valid. And then credentials are any document or information detailing a piece of information about the identity. They're tamper-proof and verifiable. They're held in a wallet. And then verifiable credential is just a data model and standard defined by the W3C for verifiable credentials. So here, the names of the parties, like issuers, holders, and verifiers, are relative here. So you can be a holder in one scenario and a verifier or an issuer in scenario. So an example scenario is a university issues credentials and you hold it, and then when you're going to a potential employer, they can verify that that your degree is valid at the point of verification. So verifiable presentations is just a process to share data with third parties. Okay, so in terms of privacy, there's emerging tech like zero-knowledge proof technology that allows you to issue privacy-preserving credentials to achieve things like anti-correlation. So if you think about, if you think about if an issuer issues credentials to a given wallet and their signature is kind of the same in each scenario, then if they collude, then they can take these individual pieces of information about you and start building a more comprehensive picture of you without your permission. So here you're just creating a unique proof each time without sharing the signature itself. And then selective disclosure is just sharing only the necessary attributes and hiding the rest. Compound proofs combining attributes from multiple credentials, and then combining it into one proof without going to another part, back to the issuer. And then predicates allows you to do things like prove that you're over 21 without sharing your birthday. So this is kind of where these examples fit in. So in vanilla verifiable credentials, right, if you have all your information kind of available for everything to be seen on there, but with zero-knowledge proofs, you can do things like selective disclosure. If I want to verify that I'm vaccinated, I can just show that my vaccination is still valid, and only show the vaccination date and not my name or birthday or anything. And then a proof of the signature for anti-correlation. So this is kind of an overview of what we've just been through. So at the bottom, you have your blockchains and verifiable data registries, which maintain your identifiers. And then the technologies involved here are like decentralized storage, peer-to-peer networks. Then you have your DIDs, which are your kind of identifier within that registry. And then wallets help you manage your DIDs and permissions and log into applications. Authentication confirms your identity. Authorization defines what resources an application can read about you. And then attestations is the claim that you're making about yourself or about another party. So putting this all together, it's just like an overview graphic of the Web3 identity stack. Cool. So this is just some of the projects that is working in this space today, tackling each of the layers. So you have your blockchains at the bottom, decentralized storage. We didn't get to cover all of the categories here, but so this is just a snapshot of where we are. It's grown a lot over the past couple years, and it's still kind of fiercely debated how we approach or come up with different standards on how protocols can communicate with each other. Privacy is still a big hot topic of a debate, and zero-knowledge technology is still being under an active area of development. So here there's some identity reputation is a very big use case for applied CKP here. I think that's it. Cool. So this presentation came from a much longer, more comprehensive article that I've written on the Web3 identity stack. So feel free to scan and kind of give it a read if you want to learn further, or I'll be around the conference if you have any questions. Thank you.